My name is Junhong from Indiana University. It's my pleasure to present our paper. We are interested in developing planning algorithms that allow robots to navigate in off-road, unstructured environments, such as Mars surface and mountain terrains. These environments can cause large robots' motion uncertainty. Markov Decision Process is a widely adopted general framework to model this complex planning and uncertainty problem. However, there are two challenges in applying this framework in the real world. First, solving MDPs requires an exact probabilistic motion model to describe the stochastic transitions, and obtaining such an exact model is extremely difficult, especially for scenarios of unstructured environments. Secondly, computing the value function over an infinite number of states is very challenging. The classic methods that use histogram-based value function representation may induce a prohibitive computational cost. We present two contributions to address these challenges. First, we realize that compared to obtaining an exact probabilistic motion model, getting only the mean and the variance of that model is much easier. With this observation, we present novel diffusion approximated Bellman equation that only depends on these two important statistics. And secondly, we leverage the kernel method to represent the value function over a continuous state space using only a finite number of characterizing states. By combining these two ideas, the value function can be evaluated analytically without needing the exact probabilistic model, which is typically very hard to engineer in practice. In the next slide, we give a brief overview of our algorithm. To compute the optimal solution, we need to evaluate the Bellman equation, where the probabilistic distribution in the red box is the motion model. We relax this traditional requirement by leveraging a diffusion approximated Bellman equation based on Taylor expansion of the value function. In this way, the resulting equation only depends on the mean and the variance of the state transition probability. To turn this equation into a practical algorithm, we need to choose a powerful and tractable representation to approximate the value function. Here, we opt to use the kernel method because it can approximate the value function using only a finite number of characterizing states. With the kernelized value function and the diffusion approximate Bellman equation, we can obtain an approximate policy iteration algorithm, which only requires a finite number of states together with the mean and the variance of the motion model. We show the process of the algorithm using a 2D navigation example. The policy and the value function are represented by the vector field and the color map, respectively. In this scenario, the value function and the policy are optimized over iterations and converges only within a few steps. We compared our method with 3 other baselines, which all use an exact probabilistic model. The 4 plots show the value function and the policy of the 4 approaches computed using 10 by 10 supporting states, which are shown in the orange dots. Our method produces smooth and correct value function and the policy, which are as good as the kernel-based method using the exact model. In contrast, the policy calculated by the grid-based approximation is discrete and requires further smoothing before applying to the robot. The neural network approximator, on the other hand, converges to a suboptimal policy. The qualitative evaluation shows the performance against the number of supporting states. By comparing with other methods, we can observe that even though our approach does not use the exact model, it can still achieve the highest expected return. This represents the best performance. We conducted simulations using datasets of Mars terrains. The results show that by following the policy computed using our method, which are indicated by the arrows, the robot attempts to approach to the goal with the minimum distance, and at the same time avoid high elevation terrains. We further leverage the flexibility of the kernel method, which allows us to select supporting states in important areas as circled in the first figure. The line bundles in the bottom 2 figures are the trajectories of different trials following the computed policy. By comparing with the policy computed from evenly tessellated states, selecting states based on important sampling obtains a better and safer policy for avoiding dangerous slopes. Please refer to our paper for more details.